Okay, today we're going to do another kind of example with Laplace transforms dealing with second order equations. In fact, we're going to consider a forced harmonic oscillator equation just like in chapter 4. It will be fairly complicated. We're going to use the computer and judiciously choose to use Mathematica in various ways to help us along. And talk about things you should be able to do for the test and also ways that I might help you on the test to make your work a little easier so it's not quite so involved what you have to do by hand. So last time we considered using Laplace transforms to solve first order forced equations where the right hand side was a discontinuous function involving a unit step function or a Heaviside function. Today we're going to do a second order equation. Second order forced equation. We're going to make the right hand side function something that we're used to from chapter 4, a cosine, which is not discontinuous, it is continuous, and we'll compare and see how well Laplace transforms does with the techniques with complex numbers in chapter 4, and I think that'll be a good review for the final anyway, to review that content from chapter 4. We'll compare, see which one seems easier versus harder, and then maybe on Wednesday we'll consider a discontinuous example where the Laplace transform definitely is the better way to go. All right, so let's see. What kind of second order forced equation can we consider? How about a forced harmonic oscillator? And let's make it be damped. Let's make it be y double prime plus 6y prime plus, I think it'll work out nicely if I make this be a 45, excuse me, 45y. And let's make it a cosine. Pick a particular frequency on the right hand side. Cosine of 5t is my forcing function. Let's make my initial conditions fairly simple. Y of 0 and y prime of 0 are both 0. This mass will not stay at equilibrium because of the forcing. So we're not going to get the 0 function here with the solution. All right. How might you approach this with Laplace transforms? Well, just like with first order equations, take the Laplace transform of both sides. Use linearity. The Laplace transform of a linear combination like that is the corresponding linear combination of the Laplace transforms. L of y double prime plus 6L of y prime plus 45 L of y. That's the Laplace transform of the left-hand side once linearity is used, equals the Laplace transform of cosine of 5t. Certainly that's something you should be able to write down for the final exam. You should also be able to, from this, use the property about how the Laplace transform acts on derivatives. This right there being s times the Laplace transform of y minus y of 0. That's definitely something you should know. By the way, instead of a note card in the final exam, you can use an entire sheet of paper front and back. But I always try to emphasize that that thing is just your security, and just writing stuff on your sheet of paper is not studying enough. You've got to practice problems. You should practice Laplace transforms enough to know this right away, that that gets replaced by that. Although y of 0 is pretty simple, that's 0, so that goes away. I could have picked something non-zero, and you should be able to deal with that.
Is it a 5L or SL?
That's an s times L of y. Thanks. And that is an s there, right there. When you take the Laplace transform of a function of t, we think of it as a function of a new variable we call s. That's the traditional notation to use. What about the Laplace transform of the second derivative? Well, the second derivative of y is the first derivative of the first derivative. So we can essentially use the same kind of property except replace the y with y prime. Like that. Once again, this thing right here is 0. Didn't have to be 0. I'm thinking it's 0, it will make it a little extra nice. But we can't stop there. We still have an L of y prime, we want an L of y. We want to solve for y, so we need to get things in terms of the Laplace transform of y. So replace this with s L of y minus y of 0, just like we replaced it with that there. And once again, this is 0. Two s's make an s squared, L of y, plus 6s L of y, plus 45 L of y equals the Laplace transform of the cosine of 5t. In other words, this can be simplified to s squared plus 6s plus 45 in parentheses times the Laplace transform of y equals the Laplace transform of cosine of omega t. Okay, that's something you should be able to do by hand. To get to here. All right, we got to figure out the Laplace transform of the cosine of omega t, evidently. There's a couple of different ways you could approach it. You could use the definition. And to do the definition, that would mean, if you're going to do it by hand, you'd have to integrate cosine omega t, not cow, cosine omega times t times e to the negative s times t with respect to t. That integral, and ultimately would it be an improper integral from 0 to infinity, pretty tricky to do by hand. In fact, if you're going to do it by hand, you'd have to use integration by parts twice. And even after doing it twice, you would have to do some tricks. If you let u equal cosine omega t and dv equal e to the negative st dt, you get an integral ultimately involving sine of omega t times e to the negative st. And then you'd have to use integration by parts again to ultimately get this in terms of another term involving the integral you want to solve for. A cosine omega t e to the negative st, and you have to actually algebraically solve that. I would encourage you to try that. By the way, can you close the door there? Thanks. I would encourage you to try that, actually. Good exercise in integration by parts. And I was going to do it, but I tested it out myself, and it took about 5 or 6 minutes for me to do. So I think it's not a good use of our time. Let's see what Mathematica gives for the answer. Of course, that's an indefinite integral, so you write a plus c. But as far as evaluating the improper integral, you wouldn't have to write a plus c. You can evaluate this from 0 to infinity, thinking like an engineer and plugging in infinity. Not literally, but it's really a limit. When you plug in infinity for t, if s is positive, which you would assume here, you get an exponential decay to 0, and this part wouldn't matter. What happens when you plug in t equals 0, and you'd be subtracting that, by the way? You get a 1 there, e to the 0. You get a cosine 0 is 1 here with a negative s there. Sine of 0 is 0, this would go away. You'd have a minus, ultimately negative s, which is the same as plus s. Don't forget the denominator there. You'd have a plus s over s squared plus omega squared. Let me write that down. Evidently, yeah, plus s over s squared plus omega squared. Is that right? I went over that pretty quick. Hopefully you've seen in my solution keys, you can actually use a Laplace transform built-in function in Mathematica. Put your function first as the first argument. Put its variable second, and put the variable for the answer third. There we go. That is the right answer. S over s squared plus omega squared. And what is omega here? I guess I should have put a 5 there. I was thinking more generally. Omega's 5 here. So when omega's 5, this becomes s over s squared plus 5 squared. It becomes that. Now we're going to divide both sides by this thing, and that's the Laplace transform of the solution. Yikes, that doesn't look like it's going to be so easy to take the inverse Laplace transform of. By the way, knowing the Laplace transform, the cosine and the sine is something you can put on your piece of paper, and I would recommend it, but again, practice stuff enough that it just comes naturally to you to just write it down. So we got to take the inverse Laplace transform of this. Can partial fractions work? Can I split this up as a sum of two fractions? Yes. However, both of these quadratics here have complex roots. The roots of that one are going to be plus or minus 5i. Can't factor that. The roots of this one are going to be complex. Think about b squared minus 4ac. 6 squared is 36 minus 4 times 45 is minus 180. You're going to get a negative 144 under the square root. So, can't factor these things. They're called irreducible polynomials over the real numbers. In that kind of situation, you should know, I'm telling you right now, and you can look this up in your calc book, that when you do a partial fractions decomposition, you have to allow for not just constants in the numerator, but linear functions of s in this case in the numerator. Which makes solving for A, B, C, and D pretty complicated. You're going to need 4 equations in these 4 unknowns. You should be able to derive equations that work, but I probably would tell you what A, B, C, and D ultimately are. How would you attempt to start it by hand? I want to inform you about that. You want these two things to be equal no matter what s is, as long as you're not dividing by 0, which is not going to happen if s is a real number. Multiply both sides by this common denominator to get cancellation. You'll get s equals as plus b times s squared plus 6s plus 45 plus cs plus d times s squared plus 25, right? Can you think that through after cancellation? And multiplying both sides of this equation, this equaling that, by that common denominator of s squared plus 25 times s squared plus 6s plus 45, and doing some cancellation. You could plug in various values of s if you want. It's not real simple because you don't get complete, things don't become 0 for real values of s. It is still beneficial, I think, to pick s equals 0 as one of the things you use. You can also expand this out to get like powers of s together. Maybe that's worth doing. Let's have Mathematica do it. I'm going to expand. I'm going to use lowercase letters for A, B, C, and D because in Mathematica, capital D, for example, is reserved, and I think maybe capital C is as well. So I'll use lowercase here. Expand as plus b times s squared plus 6s plus 45 plus cs plus d times s squared plus 25, right? No, okay. 25. Okay, so your constant term, if you do this expansion, the expansion way, 45 plus 25d. Your s term has a coefficient of 45a plus 6b plus 25c. Your s squared term has a coefficient of 6a plus b plus d, and your s cubed term has a coefficient of a plus c. Coming back over here, all those coefficients except for the s one have to equal 0. The s coefficient has to equal 1 because that's what's on the left-hand side. So you get a system of 4 equations and 4 unknowns, 4 linear equations. Solving that by hand again would be unpleasant. Those of you who are linear algebra should know how to do it pretty quickly with row operations, but that's not something I'd have you take the time to do on the test. Probably I would tell you what A, B, C, and D are, is what I'm thinking. But you should still be educated about the method here. Again, 45b plus 25d must be 0. That's the constant term. 45a plus 6b. I don't need parentheses there, but I did it anyway. That must equal, one more term, plus 25c. That's the term that must equal 1. Because that's the coefficient in front of the s. And that's got to equal 1. Okay? So, put the 1 in there. The s squared term, its coefficient is 6a plus b plus d. That's got to equal 0. It's amazing when you can't see your typing. It's easier to make a mistake. That's the s squared coefficient. The s cubed coefficient is a plus c. All right, so I think this is all right. Looks like A is 1/65, B is 3/26, C is negative 1/65, and D is negative 27 over 130. Actually, I know a quick way to check this all at once is with something called a part in Mathematica. A part will do partial fractions. I think I use that in my solution key as well. That's the way we can check the work here. Negative 27 over, okay, let's do this one first. 2 over 130 is the same as 1/65, that's the A. 15 over 130, divide the top and the bottom by 5. 15 divided by 3, 5 is 3. 130 divided by 5 is 26. Negative 2 over 130 is negative 1/65, and negative 27 over 130 can't be reduced, it's right there. All right, so this looks right. So I've got, let's write it this way. Actually, I think I'll do it more like Mathematica's apart did and write these as fractions over 130, even though some of those fractions can be reduced. Put a 1 over 130 in front, at least initially. So this is the thing we've got to take the inverse Laplace transform of. Still doesn't look real easy, does it? Seems like the fact that the Laplace transform of cosine of 5t equaling this might be helpful, at least for this one when you think about the s part. In fact, let me go ahead and break this into 4 fractions then. There's 2 fractions whose sum is the first term. Again, I think I'll keep everything over 130 and not reduce, just to, I think that'll keep things a little simpler in the end. I know this is a complicated process. Lots of different things to think about here. You may want to watch the video again, besides being in class here today. So we've broken it up into simpler looking pieces at least. Yeah, I'm looking at this one and comparing it with this fact and saying that looks good to take the inverse Laplace transform of. This one looks simpler than that one because there's a 1 there instead of an s. Is it related to the Laplace transform of cosine? Actually, no. But it's related to the Laplace transform of something similar, the Laplace transform of sine omega t, for a general omega, turns out to equal omega over s squared plus omega squared. Whereas the Laplace transform of cosine omega t was s over s squared plus omega squared. I'm not deriving that. I forgot to mention the other way to derive this fact here. The book uses a little trick, and I wanted to show you that trick, but I think for the sake of time, I'm not going to have time to do it. There's a trick in the book for deriving this Laplace transform in a pretty quick manner, using knowledge that the cosine omega t solves a pretty simple second order differential equation. Just let you read about that in the next day or two. I would encourage you to do that. Yeah, it turns out the Laplace transform of sine omega t is this. In our problem here, omega is 5. So, let me write 15 as 3 times 5. That was a 15 there before. Now I'm going to separate it as 3 times 5. Now I've got 5 over s squared plus 25. Omega is 5. I've got an omega there and an omega squared there. So this looks good too. These two don't look so good though. How do you deal with those? This gets even trickier. Okay, pay good attention here. Again, s squared plus 6s plus 45 has complex solutions. However, if you were going to graph that function, s squared plus 6s plus 45, without using calculus, think back to your pre-calc days, you'd want to find the vertex of this, and the way to do that is with the method of completing the square. I'm not actually going to graph it, but think back to your pre-calc days. Don't take the derivative of this. You've got to pretend you don't know how to take derivatives. How do you find out where the vertex of this parabola is? You have to complete the square, which means since this coefficient is 1, you can just take this number, the 6, divide it by 2 to get 3, square that number to get 9, and write 45 as 9 plus 36. Just a little trick to help you realize, to help you make a perfect square there. S squared plus 6s plus 9 is the same as s plus 3 quantity squared. And 36 is the same as 6 squared, and that's going to be helpful to realize too. And when you take a look at this and think about replacing this down here with that, that should feel good to you, because then you've got something squared plus something else squared, which is more reminiscent of what's going on with these fractions. So that should seem good, maybe not easy, but better at least. I'm going to go ahead and do that. In fact, let me just focus on each of those terms individually. Long process here. Again, I've got to do things to help you here along the way. But you should study this enough that you can follow all these details. If you haven't studied the book yet, do so. So I've got this 2 over 130. I won't bother with the minus signs here. I will eventually put them back in. 2 over 130 times s over s squared plus 6s plus 45, which is s over s plus 3 squared plus 6 squared. It's going to turn out to be helpful to do a little trick there as well. It's going to turn out that because this is an s plus 3, it's going to be beneficial to replace the s there with s plus 3 as well, so you get a match. However, you can't just do that willy-nilly, because then they're not equal. Since I added 3 up there, I also have to subtract 3 from another fraction that's similar. To compensate for that. Again, my goal was to get a match here and here. Kind of reminiscent how there was a match here and here. The inverse Laplace transform of this thing involves the cosine function. Turns out the inverse Laplace transform of this thing also involves the cosine function. But how do you adjust for the s plus 3's is the question. Let me also do something similar. I guess, well, with the other one I don't think I need to do something quite so tricky. The other one is 27 over 130, 1 over s plus 3 squared plus 6 squared. Actually, it still is a little tricky, what I'm about to do. It turns out with this one, since there's a constant up top, that's reminiscent of the fact that this one has a constant up top. The inverse Laplace transform of this thing involves a sine, and the thing up top is the square of that, or excuse me, the square root of that. This is the square root of that. The 25 here is like the 36. It's going to be a good idea to put a 6 there. This method probably is not as good as the chapter 4 method. I think we can already evaluate as far as difficulty level. And that chapter 4 method was tricky enough as it was. Again, I'll give you help here. So this Laplace transform method for this kind of problem is not superior, it's inferior to the chapter 4 method. But if we have a discontinuous function there, this might be superior. And we'll probably consider an example like that on Wednesday. I want a 6 to be there, but I got to compensate. 27 is 6 times what? 4.5. Right? Yeah. Put a 9/2 here. Crazy, huh? Now I claim I can find the inverse Laplace transform of these things pretty easily, though I do need one more fact. I think this is the final new fact of the entire semester. Maybe. Might have some new facts on Wednesday. Maybe this is the last new fact to know for the entire semester. Suppose the Laplace transform of some function little f of t equals some function of s, call it capital F of s. Then it turns out that the Laplace transform of e to the at times f of t is capital F of s minus a. This fact can be derived pretty easily. It's not too hard to derive. It's just a matter of doing a little rearranging for this integral here. Assuming you're at a value of s where it converges. Using properties of exponents, you can rewrite that integral like this. There's the function you're taking the Laplace transform of. What do we have here? We have the function f of t times this dt, you're integrating. Whatever the quantity is right there, this is a Laplace transform of f at that value, which is exactly that. How is this helpful here? Take a look at this here and here. You've got s plus 3's there, there, and there. S plus 3 is the same as s minus negative 3. Think of the negative 3 like the a. You really have a Laplace transform of s minus a for the cosine function and the sine function. So the inverse Laplace transform is going to involve the cosine and sine function with an extra factor of e to the at in front. Any equation like this can be thought of as in terms of inverse Laplace transforms too. So what do we have here? Are we almost done? I think we can write down the answer now pretty quickly, actually. Erasing the differential equation. Y is the inverse Laplace transform of all that stuff, of this whole thing here. Can I save time that way? The inverse Laplace transform is linear. You should know that. Therefore, you can write this as 2 over 130, which is 1/65, times the inverse Laplace transform of s over s squared plus 25, plus 3 over 130 times the inverse Laplace transform of 5 over s squared plus 25. Those are the easy parts. Okay, careful. Minus the inverse Laplace transform of this, which is the inverse Laplace transform of this minus the inverse Laplace transform of that. Should I go ahead and distribute the minus sign through? Careful. Oops. Inverse Laplace transform of s plus 3 over s plus 3 squared plus 6 squared. Minus, again, a 2 over 130, which again can be reduced to 1/65. Inverse Laplace transform. Oh, one more place to be a little careful here. Really want a 6 up there. Let me go ahead and make 2 times 3 be 1 times 6. Make this a 1 here. You're not writing in pen. Looks like you are. This was originally a 2 times 3. I want to make it a 6 because of the 6 there. And I almost made another mistake. I'm subtracting this whole thing, so now I have to add there. I'm subtracting because of the minus sign there. Oh, so many places to make mistakes. Let's see, 6 over s plus 3 squared plus 6 squared. And then minus the inverse Laplace transform of that, minus the inverse Laplace transform of this. Minus 9 halves over 130 is 9 over 260. Inverse Laplace transform of 6 over s plus 3 squared plus 6 squared. And actually, these two things can be combined, this and this, into one term. This is 2 over 260 minus 9 over 260 is negative 7 over 260. I hope I haven't made a mistake. Does anybody feel like I've made a mistake anymore? You able to stay awake here? Whew, this is quite a calculation. We're almost done. Now I think we can just write down the answer, hopefully. And if we made a mistake, hopefully I can figure it out where it was. Inverse Laplace transform of this is cosine 5t. 2 over 130, which I'll now reduce to 1/65. Cosine 5t comes from that one. Plus 3 over 130 cannot be reduced. Sine of 5t. And actually this thing here, that's yp. That's the particular solution, the forced response to the original equation. Minus 2 over 130 is 1/65. Inverse Laplace transform of that. It's like you have the inverse Laplace transform of s over s squared plus 6 squared, but replace s with s plus 3. The inverse Laplace transform of s over s squared plus 6 squared is cosine 6t. That's going to be like the f of t, but I need an extra factor of e to the at in front of it, where a is negative 3. S plus 3 is s minus negative 3. Wow. Okay. yeah, e to the negative 3t cosine 6t. An exponential decay. That's part of the YH with the other method. We also have initial values here. And again, these two can be combined as negative 7 over 260, which cannot be reduced. You got a 6 over s plus 3. That's, if this was just an s squared plus 6 squared, the inverse Laplace transform would be sine of 6t. Because of the s plus 3, once again, coming back here, you need an extra factor of e to the at in front, e to the negative 3t. Sine of 6t. I think that does it. All right, let's see, are we right? DSolveValue. Y double prime of t plus 6y prime of t plus 45y of t equals cosine, what was it, 5t? Forgot. There it was. 5t. Y of 0 and y prime of 0 are both 0, and you can do that in a compound way like this. You don't have to put two separate equations when they equal the same thing. You can do that all at once there. Comma y of t, comma t. I think initially here it's not going to look so nice. Dice. So did we do it wrong? I don't think so. If you do trig reduce applied to that, it does look better. And now expand. Do we have a match? 65 cos 5t, 3 over 130 sin 5t. Yes! Give me a hand. Oh. So I got to give you help with that. But you should know the big picture and be able to fill in some of the details. Where would I give you help? I give you help probably in telling you what the answer ultimately can be written as. This, although you'd want to modify these two things in terms of what I erased. This stuff. You should know the inverse Laplace transform of that whole thing is the answer, and the inverse Laplace transform is linear. And once you have this kind of expression, you should be able to use this property here, which is called shifting on the s-axis, capital F of s minus a. The property from last Friday was shifting on the t-axis. You should be able to use that property to find this final answer there. Wow. Definitely the chapter 4 method is better. But on Wednesday, we will make the right-hand side forcing term be discontinuous, and then Laplace transform is the better way to go. Wow. Okay, can we do something else today? Yes, I do want to go back to trapping readings and talk about things you should be able to know and do for the exam. In the extra reading about trapping regions, you should certainly know the Poincare-Bendixson Theorem and how to apply it with fairly simple examples, hopefully. I guess the fairly simple example is the kind I'm talking about here with example 3. Again, this theorem says if you've got a planar vector field, so it's two-dimensional, R2 represents the plane. Let this fancy R be a trapping region, and any of the senses above that were in the reading, I had sort of 3 different senses of what a trapping region means. The simplest kind being what I called a smooth transversal trapping region. I'll talk about what that means when we consider the example. If the system has no equilibrium points inside the trapping region, then there must be a periodic solution. Okay? This is actually not the way the Poincare-Bendixson theorem is usually stated, but it's equivalent to it in its sort of simplest form. And the most significant form in terms of how you'd want to prove the existence of periodic solutions, which is a pretty significant thing. Okay? To show that periodic solutions exist in general, if that's a difficult thing to do, this is one of your main tools to do that kind of thing. The simplest kind of example that I can think of is example 3, although it's not easy. If you think about a system of differential equations in polar form, like this, where r and theta are polar coordinates, dr dt is this, d theta dt is 1, and if you think about what that would mean in an xy plane with a polar grid imposed on it, if you think about it in the right way, it should be intuitive that a periodic solution exists along the circle of radius 1 centered at the origin, the unit circle. So we've got an xy plane here. You have to imagine a polar grid imposed on this. So you have these different angles, which you can take the common angles of 30, 45, 60, if you like. You can also add in other angles. You've got circles of various radii centered at the origin as well. Let's pretend this is a radius of 1 right there. There's a real rough drawing of a basic polar grid on the xy plane. d theta dt for this differential equation is constant. It's 1. In other words, theta as a function of time is really t plus the initial value of theta. So theta is going to increase in a linear way. You're going to get a rotation of solutions around the origin counterclockwise at a constant angular velocity. 1 radian per second, if you like. dr dt, again, is r times 1 minus r, which is r minus r squared. You could solve that equation actually with separating variables and then using partial fractions to integrate. We did that before, second day of class, third day. But let's not do that. Let's just think about it intuitively. This right-hand side function is positive if r is between 0 and 1. So when r is between 0 and 1, r is an increasing function of t. dr dt is positive. And it's negative if r is bigger than 1. So solutions are decreasing for initial conditions that are bigger than 1. You always have to be rotating around the origin at a constant angular velocity. That's 0 when r equals 1. The function where r always equals 1 and theta is something like that is a solution, and in fact that's your periodic solution. The origin also is an equilibrium point. If you start out close to the origin in between here and here, you're going to rotate counterclockwise in a spiraling way. The origin is going to be a spiral source. And if you start out outside the circle of radius 1, you're going to spiral in toward that periodic solution. R has to decrease. Can you convert this to rectangular coordinates? Yes, though I wouldn't expect you to be able to do that in the test because it's just a little tricky, a little too tricky. I did it here using the chain rule and product rule. You can take a look at these things and I think you can all understand this. I ultimately wrote this in terms of rectangular coordinates, and the rectangular coordinates looks kind of complicated. The only thing that involves square roots. That's because r is the square root of x squared plus y squared. That is the same system in rectangular coordinates, and the phase plane can be made in the usual way for stream plot and vector plot to look like this. The green region is supposed to be a trapping region. In fact, it's supposed to be a smooth transversal trapping region. The word smooth means the boundary curves are smooth curves, no corners. Transversal means all the solutions enter the trapping region in what's called a transverse way, non-tangent. There are no solutions that come in and then sort of enter in a tangential way like that. Watch my finger here again. There are no solutions that come in like this and sort of touch the circle tangentially before going in. They're all entering in a transverse way is the word people use. So you should know that's a trapping region. You should be able to verify the origin is the only equilibrium point, and therefore there are no equilibrium points inside this trapping region. Therefore, by the Poincare-Bendixson Theorem, there is a periodic solution. In fact, we can even find its formula in terms of polar coordinates. And because of that, you can even find it in terms of rectangular coordinates. What else should you be able to do? You should be able to check that this is a trapping region according to that condition I had about outward pointing normal vectors. Here's what I mean. We're doing it in time. Got about 5 minutes here. What's the vector field f of y? In terms of rectangular coordinates, look at these equations here. It's x minus y minus x times square root of x squared plus y squared, which I think I will just replace with an r when I do the following calculation. And then the second component is x plus y minus y times r. Replacing that with an r will make the calculations a little simpler looking. What's an outward pointing normal vector? Well, it depends on whether you're at the outer boundary or the inner boundary of this annular region. By the way, the radius of this inner circle is 1/2, and the radius of the outer circle is 3/2. If you're along the outer circle, an outward pointing normal vector has to point out of the region this way. It is normal, so it's perpendicular to the curve at every point, y. For the inner circle, the outward pointing normal vector would have to go into the circle. It's pointing out of the trapping region. What would be an example of a normal vector here, say an outward pointing one? It's simpler than you might think. There is an outward pointing normal vector along the outer circle. At any point x, y along the outer circle, draw the position vector for that point, except based at that point instead of at the origin. It's going to be an outward pointing normal vector. For the inner one, we call this n out. For the inner one, you can just use the opposite of that. N in, negative x, negative y. What was the condition that guarantees that this is a trapping region when you relate these vectors? The dot product should be negative along the given curve, because that's going to mean the angles between the outward pointing normal and your vector field is bigger than 90 degrees, and that's going to mean your vector field is pointing into the trapping region in a transverse way, a non-tangential way. You can have other kinds of trapping regions where the vector field doesn't go in doesn't go in transversely, but this is the simplest kind. So let's stick with this simplest kind. So how would you take this dot product? Let's do the outer one. With the usual formula for dot products, which most of you probably know. If there's anybody who doesn't, here's what you do. Multiply the first components and add the product of the second components. That's the dot product, if you've got the components. So I take the first component of f, x minus y minus x times r, and multiply it times the first component of n out, which is x. Add the product of the second components, x plus y minus y times r times y. Simplify. Hopefully you get some cancellation. You get x squared minus xy minus x squared r plus xy plus y squared minus y squared r. The xy terms go away. Let's see, how should we think about this here? You really got an x squared plus y squared minus x squared plus y squared times r. This can be thought of as r squared. This can be thought of as r squared. You really have r squared minus r cubed. R squared times 1 minus r. Along the outer boundary, r is 3/2. When r is 3/2, this thing is negative. Done. For the outer boundary. If you do it for n in, you're going to get the same thing except with a minus sign. Yeah, you ultimately get r cubed minus r squared. I'll let you check that out. R squared times r minus 1, and if r is 1/2, as it is along the inner boundary here, then this thing is also negative. Okay? So that's an example of something you should be able to do. This is the simplest kind of example that I can think of. So maybe I'll make your example in the final if I give you something like this, slightly more complicated. But probably not much more complicated. I do want to spend more time on Wednesday also talking about example 4, which is a more significant application. But we'll save that for Wednesday. Have a good day.